Hello, bonjour, guten tag, ciao, buenos dias, boa tarde, ni hao, dzień dobry, privyet, and good day, mate. I believe those greetings cover about 95% of the pre-registered webinar audience. I'd like to apologize for my poor pronunciation of some of the greetings, but I would like to thank all of you around the globe for joining us on this webinar. My name is Timothy Gotsick, and I look forward to telling you about how LUX technology enables better Flexo print. First, I'd like to talk a little bit about printing technology in general. When package buyers are selecting a method for printing their packaging, they have a choice of a number of different technologies, and we try to keep this in mind when we're designing our research efforts to improve flexography. In particular, as you look at how the different technologies stack up in terms of quality and cost, which are usually foremost in buyers' minds, this is how we see them. Digital is a little bit unique, so I have it separated out because its quality and cost differ depending upon the application and the run length. But when you look at the quality rankings of the others, typically flexography falls somewhere below that of gravure and offset, who are regarded as having the highest resolution and greatest quality of all the print technologies. In comparison, when you look at cost, again, digital stands somewhat separate because it's so dependent on run length. But here, flexography has a much better profile and often is considered to have the lowest cost of any of the package printing technologies. The obvious comparison here is that if we could find a way to make flexography have a quality that was equal to or better than gravure and offset, we would have a very competitive technology. And fundamentally, if we had equal quality combined with a lower cost, this would end up in more packaging being printed by Flexo, which is of interest to virtually everyone listening to this call. Now, let's talk a little bit more about print. Print is a two-dimensional medium. And so when you're looking at a package or anything that's printed with a halftone image, you're looking at a print that is created by the position, the color, and the size of little dots that are overlapping one another. But it's fundamentally a two-dimensional problem that you have to solve. As long as you have the right size of dots, the right color, and they're in the right places, you'll get the right image. We use screening to address these two-dimensional issues, where in the conversion of a continuous tone image like that found in nature to a halftone image like that used to print on a package, you go through a raster image processor, commonly known as a RIP, in order to create that. There are a number of different algorithms that are used to determine the placement and size of the dots. They range from very simple ones like AM screening to much more sophisticated screenings that have been developed in recent years. But fundamentally, this is a software issue, determining the size and position of the dots. However, when you look at a flexographic plate, you're not confronted with just a two-dimensional problem. The dots have size and position in the XY plane, but they also have a third dimension, height, which means that the shape of the structure underneath the top of the dot is important as well. Now, addressing this third dimension is really what comes into play when we make a plate. In moving from a file to a relief plate, there are three places where we can have an impact on the dot shape. The first is during the image transfer to the mask or ablation step, with the laser type that's used and the resolution or spot size of the laser can change can make the hole in the mask different, and that can influence the dot shape. The second stage is during the image transfer to the photopolymer or UV exposure step. Here, the chemistry of the plate fundamentally can change the shape of the dot somewhat, and also the UV exposure nature, its collimation, its wavelength, its intensity, things like that can have a pretty large effect on the shape of the dot that results. Also, there's a little bit of an effect from the processing step where, depending upon whether you're using a solvent or thermal processing of this plate, you can create slightly different dot shapes. But fundamentally, in comparison to the screening issue, the third dimension that we're dealing with here is determined by hardware, which is really what determines the shape of the dots. We believe that Flexo is all about the dot, and that really the interaction of that three-dimensional plate dot with the two-dimensional substrate is where the magic and mystery happen. The three images that are shown on this slide really capture the entire value creation mechanism of flexography, which consists of the three relatively simple but rapidly occurring steps of deposition of the ink on the top of the dot, the contacting of the ink dot with the substrate, and the release of ink from the top of that dot onto the substrate. Fundamentally, this is where everything happens, and we believe that if you make the right dot on the plate, then the best print will follow. This begs the question of what is the right dot? Well, there's a simplistic answer to it, but and I'll give it to you, but it helps to explain the perspective that we take on developing the right dot, which is that fundamentally the right dot is the one that gives you the print you want. And so instead of just making dots and arguing over their structural characteristics, we always are sure to print all the dots we make to understand exactly what their impact is on the final product, because at the end of the day, a dot is just a way of making a print. This is an example of the kinds of dots that we can make, and this is just a subset of hundreds that we've been able to make over the last several years. These are all actually made on the same photopolymer, so it shows that it's possible to get a wide diversity of different dot shapes, even out of the same chemistry. We have printed all those dots and more, and I can say that from our experience, we found that there are lots of dots that do work, but some dots work better. And there are 4 factors that we believe are most important for making a good printing dot. The first is dot surface morphology, which is just a fancy way of saying the shape of the top of the dot. It can be flat, as shown in this picture, or it can be rounded, or it can be anything in between. The edge definition is also important. The edge is essentially the definition between the printing surface of the dot and the support structure or side of the dot. And once you're able to define those as 2 separate areas of the dot, you can independently optimize the 2 and make each perform its function best. The third is the valley depth. The valley depth is the depth between the top of the dot and the bottom of the valley in between it and the dot next to it. This is very different from the relief of the plate. The relief of the plate is determined by the height of a solid to the floor of the plate, which, for instance, in a digital plate might be 20 mils. The valley depth in a process area between 2 dots is usually much shallower. It can often be only 1 or 2 mils deep. Having a deeper valley depth, we believe, prevents interaction of one dot with the one next to it and leaves a little extra room for ink to accumulate if the plate is being slightly over-inked. The fourth factor that we believe is important is the shoulder angle, which is the angle between the dot surface and the supporting shoulder. As with the edge definition, this is essentially a measure of how separate the two portions of the dot, the print surface and the support structure, are, and again allows you to optimize the 2 independently. In recent years, there's come to be a lot of argument about what is the right dot, and the 2 that have emerged, general classes of dots that are being discussed a great deal these days, are essentially the round-tipped and flat-top dot that you see presented on the screen. Let's talk a little bit about what's different between these 2 dots, and then I'll show you some of the ways that they differ in performance. On the left, you see the typical standard digital plate round-tip dot, and on the right, you see a flat-top dot. And both of these can be produced by a digital workflow, which is, of course, very important since most people have gone to digital workflows for its efficiency and ease of modification. An interesting difference between these 2 is the fact that the dot height of the standard digital dot is actually slightly below that of a solid in the same plate. This is due to the effects of oxygen, which tend to recess the smallest dots slightly compared to the solids. In contrast, the flat-top dot, even at its very smallest size, has a height that is what we describe as type high, meaning that the smallest dot top is exactly the same height as the solid within the same plate. So all of the surfaces are at equivalent height in a flat-top dot plate. As far as mechanical stability goes, obviously standard digital dots are more than stable enough, as millions and millions of feet have been printed with them. However, everyone knows that they're also prone to becoming unstable, particularly in the smallest highlights, if they're not properly formed or if you don't get the bump curve right. I'll talk a lot more about the bump curve in coming slides. For flat-top dots, they're inherently somewhat more stable because they have a broader base and they have a better support structure than the standard digital dot. I'll show you some pictures in a bit that give you an idea of exactly how great this difference can be. And then finally, the mask-to-plate imaging between the 2 dot types is considerably different. Because of oxygen inhibition that I mentioned before, the standard digital dot requires an adjustment factor, usually called a bump curve, to compensate for the oxygen inhibition. This allows you to actually form the smallest dot that you want, but in order to do it, you kind of have to put a fudge factor into the mask to make it work. In contrast, the flat-top dot has a 1-to-1 reproduction profile, which means that whatever size hole you burn in the mask, you will get the same size dot in the photopolymer. This takes away the issue of the bump curve entirely. We have a solution that we believe delivers flat top dots in a high-quality manner and fundamentally enables higher quality print. The name of this technology is LUX, and I'd like to describe it to you in greater detail now. If you look at a standard digital plate workflow, most of us are familiar with this. You take the digital plate, you ablate the image into it, you expose it through the mask, and then process it normally. Adding LUX technology to this workflow only involves the addition of a single step, where after the image is ablated into the mask, you laminate a LUX membrane on top of the plate and then expose through the membrane. The membrane is then removed manually after exposure and processing occurs as normal. So it's a single addition of a step. The step takes about 2 minutes, and with the additional plate handling, takes maybe 4 to 6 minutes total. The LUX membrane and the lamination are proprietary patent-pending processes developed by MacDermid. This is a picture of the LUX laminator, and I will describe it in more detail as we go on in the presentation. Let's talk about the advantages that LUX potentially offers. I believe that they fundamentally fall into 3 classes: quality, consistency, and versatility. First, let's discuss a little bit about the quality advantages of LUX. The LUX process produces a fundamentally different dot shape than does the standard digital process, but it uses the same plate and most of the same workflow. These pictures show the difference that's created by the use of the LUX technology. Both of the pictures are made of digital max, a 60-durometer digital plate, and both were made with a 5% hole in the mask. As you can see, the standard digital plate creates a very small, fine-tip, rounded top dot from this 5% hole. It's probably a 1% or maybe even slightly below a dot on the plate. In contrast, the same plate made with the LUX technology creates a much different dot shape where the 5% hole in the mask has been converted into a 5% dot on the plate. You'll note that the shoulder angle, particularly up near the print surface, the flat top print surface, is still quite steep, but below that it broadens out into a much more considerable base for that dot. All of the factors that I talked about before, the flat top dot, the very good edge definition around it, the steep shoulder angle, and the deep valley are apparent in those dots. And this applies not only to dots, it also applies to other features in the plate like the type. So that in type you can see finer features, you'll be able to hold sharper character edges, and the reverse type tends to be deeper using LUX than it is with the standard digital process. Now let's talk about the gain characteristics and their comparison with a standard digital plate. Here we see the same photopolymer made with a standard digital workflow and made with a LUX digital workflow. They don't look wildly different, but I'd like to call your attention to the highlight region where the effects of LUX are most startling. If we blow up that region and look at it, it's interesting. The standard digital plate has a slightly higher gain at every step shown here. The interesting thing is that if you compare the size of the dot on the plate, which is what's represented on the x-axis, to the size of the dot that's printed, represented on the y-axis, you'll find that LUX actually prints smaller dots. And this despite the fact that the dot measured on the plate with the LUX plate looks to be larger. Let me explain. If you look at the very smallest dot on both curves, you'll see that the standard digital plate produces a plate dot that measures 0.6%. However, when that 0.6% dot is printed, it results in a 7.4% printed dot. In comparison, the LUX digital plate, exact same photopolymer, creates a plate dot that measures at 1.2%, but prints to only 4.6%. This goes back to my contention before, that the right dot is the one that gives you the right print. And in this case, if you want the smallest highlight, LUX makes the right dot. This continues on throughout the tonal range depicted here, where you can see that even at the next step, where the standard digital plate gives a 1% dot that prints to 8.8%, the LUX digital plate gives a 2% dot that prints to only 7%. This has many advantages. It can expand your printed gamut, and it reduces the hard edge and improves the fade to zero for vignettes. Let's talk a little bit about how this improved highlight detail arises. I mentioned before the concept of the use of a bump curve, where you have to take somewhere between a 4 and a 10% bump on the plate in order to make a 1% dot. This means, for instance, taking the middle of that range, that I have to burn a 7% hole in the mask in order to create what measures as a 1% dot on the plate. This is very different from what happens with LUX, where you make a 1% hole in the mask and you get a 1% hole in the plate. It's one-to-one imaging between the mask and the plate. In addition to basically reclaiming that 4 to 10% of the tone range that you had to sacrifice with the bump curve, this results in greater consistency where you don't have to worry about chasing the bump curve around. The bump curve is known to vary within plate-making operations and certainly between different plate-making operations, and all of that is eliminated. Perhaps it's best seen by looking at the dots that result from a standard digital plate and a digital LUX plate. The standard digital plate is shown on the top row of dots, a 1%, a 5%, and a 10% dot on plate. And you can see, in addition to the very different dot shape from the LUX digital dots shown below, that there really isn't as big a difference in the size of the 1% dot and the 10% dot as you might expect. It certainly doesn't look like that 1% dot is only a tenth the size of the 10% dot. In comparison, on the lower row, the LUX digital dots, it's very clear that that 1% dot has a much smaller area at its print surface than does the 10% dot, and much more in ratio of the proportion. This allows you to reclaim several of the steps of the tonal range that are lost by the use of the bump curve. I'm going to show some print samples now, and I'm always cautious about doing this in presentations because obviously the depiction of the print sample on the screen does not do justice to the print sample itself. I would encourage you that if you're going to be able to attend the North American FTA conference coming up in May, that you stop by our booth and actually see some of these print samples so you can see exactly what the results are for yourself. If you're unable to attend the FTA conference, please contact your MacDermid Printing Solutions representative, and they'll be happy to come with a portfolio of LUX print samples to show you this. So here's the first example. This particular printer, and this is a commercial job, moved this job from 125 lines per inch to 150 lines per inch, got better highlight detail, particularly in areas like the very light area inside the fish there and the lemon adjoining it. And we're able to do this with no changes whatsoever required in their print operation. So they got to a higher line count and a higher perceived print quality, and they were able to start talking about competing with gravure work now because they realized that they could raise their quality level beyond what they were able to do before. This shifting of gravure to Flexo work has a lot of benefits. The two most important ones are an improved cost structure for the printing, where a job-printed Flexo, particularly in a short run, can be maybe half the cost of the same job-printed gravure. And there's also the environmental advantages of using Flexo instead of gravure, where Flexo has been shown to have a lower environmental footprint overall than gravure print. And again, I emphasize this jump was made without any changes in the print train whatsoever. So hopefully I've shown you a little bit of why we believe that there are quality advantages to LUX. Let's talk now about some of the consistency advantages that LUX can bring as well. First, a test. Don't be worried, this won't be too hard. Look at both of those dots and tell me where is the edge of the print surface on each. I'd say it's pretty easy to guess where the edge is on the flat top dot. It's that distinct angle that we have at the intersection of the dot shoulder and the dot top. In comparison, finding the edge of a round surface is a little trickier, and I suspect that most of us can't really define exactly where it is. Now, I'll submit to you, if you and I can't define the print surface of the dot on the left, how is the ink supposed to know? Well, in practice, the ink knows by how much we impress it into the analox and onto the substrate. And so if you look at a round top dot, as shown in the picture here, and you look at the different impression levels, which I've labeled 0, 1, 2, and 3, impression level 0 is a point where the dot isn't actually touching. As I mentioned before, because the dots, standard digital dots, are recessed below the level of solids, you may see on press that your solids start to come up and print before any of the dots do. That's a great example of that maybe half mil difference in height that you'll see. But as you move into further impression, you'll start to see the dots beginning to ink up. The interesting thing about a rounded surface, though, is that the more you press it, the larger the dot becomes. And so essentially, the dot size is being varied and controlled by impression rather than the actual defined print surface in a geometric sense. Let's look at some data that shows how this works. This is a print of digital MVP, which is a 50 durometer digital plate from MacDermid, and it shows it at the lower curve. The green curve is the optimal impression, and the upper reddish curve is the optimal impression plus 6 mils, which is quite a bit. And you can see that there's some substantial gain, particularly in the mid-tone that results. Between 30 and 50% tone scales, you're looking at somewhere between 10 and 15 percentage points increase in gain as a result of the increased impression. If you look at the same exact photopolymer plate, but this time processed as a digital plate with the LUX technology, you'll see that there's considerably less impact of impression. And now, between 30 and 50%, you see a much smaller difference between the two curves. Let's blow this up so you can see it better. And you'll see that LUX, on the same photopolymer, reduced the dot gain caused by impression by anywhere from 30 to 60%, where in the upper standard digital plate, you have a 10 to 15% percentage point increase in gain. The LUX plate in the same region has only about a 5% increase. What are the advantages of this? Well, fundamentally, it means that the dot gain is less sensitive to impression and allows greater consistency. It's very difficult to hit the same impression over and over and over again, but with LUX, you don't necessarily have to because you're not going to see a big difference in it. This is also going to mean that over the course of the run, you're going to have to make fewer stops for adjustment. You're going to be able to maintain longer runs, which is ultimately more profitable for the printer. Now let's talk about the effects of plate wear. Over the course of a long run, it's not impossible to see wear in the plate, and this is an example where I can show a production run that was done in a commercial plant using Digital Max, a 60 durometer plate. They're 107-inch plates, thickness plates. The plates were run almost 900,000 linear feet on a shrink film using a solvent-based ink. And if you look at the picture of the highlight dots shown at the beginning of the run and the end of the run, there's definitely some evidence of wear in the plate. Not dramatic, but you can see that the dots are a little bit shorter. Their tips are not quite so well defined at the end of the run as they were at the beginning. However, if you look at the print that resulted at both portions of the run, you'll see that although there's some evidence of wear in the plate, there's no evidence of it in the print. The dot sizes are virtually identical from the beginning and the end of the run. So your color, your quality of your vignette fade was essentially kept constant throughout the run. Another advantage that the printer cited was that they didn't have to stop the press to clean these plates, like they might have to do with standard digital plates. This was an estimated 3-hour savings for them, which is 3 hours where instead of performing maintenance on the press, they were actually printing and making money with it. Let's look at some of the reasons why we might see better consistency and clean printing from the LUX plate compared to the standard digital plate. Again, if you look at the profile of the two dots that I'm showing there, the standard digital and the LUX digital, you'll see in particular that the deeper valley depth that I spoke about earlier is very evident. And if you take outlines of both and superimpose them, you can see how much this is. This is pretty substantial. You're looking at something probably 25% of the total valley depth is greater in the LUX plate than it is on the standard digital plate. So essentially, if you do have any ink that builds up in between those dots, it's going to take a good bit longer for it to build up to the point that you're going to see dirty print or dot bridging. Okay, well, we've talked about quality and consistency. Let's now talk about the versatility of the LUX technology. This is an example of a printer who successfully moved gravure job to Flexo by moving to LUX. Again, this was a job where there was an increase in line screen from 125 to 150 line screen that was made possible through the use of LUX without any other changes to the print train. This was actually was intended as the first production scale test of LUX in this particular printer, but the brand owner responsible for the feed bag that you see there was present and was so pleased with the print that they signed off within a half an hour and the entire job was run using the LUX plates. The other nice thing that the print operators cited was the fact that they had to use less impression with the LUX plates than they did with standard digital plates. This, again, is a consequence of the effect I talked about before, where all of the elements in a LUX plate are type high or at the same level. So all of them come up to color at the same time, and you don't have to over-impress one part of the plate in order to get the highlights to print. This particular printer has continued on very successfully with the LUX technology and is now moving multiple jobs from gravure to Flexo, which results in substantial savings over the course of the short print runs that are common at this place. Here's the other end of the spectrum. This is a LUX user in the narrow web. As is common in many narrow web accounts today, this printer has, in addition to multiple Flexo presses, an HP Indigo digital press as well, and they do move jobs back and forth between them. The interesting thing about this particular comparison is that both of these prints were made with the exact same file. There were no changes made in moving from the Flexo press to the digital press. This gives this printer the option of moving jobs based on the economics of the print run rather than on the quality obtainable. The quality is virtually indistinguishable between the two, with highlights showing very, very good definition in both. If anything, from looking at these, I'd have to say that the color saturation is a little better on the Flexo sample. But this opens up a whole new world for this printer because they can now make decisions based on, rather than making decisions on limitations, they can make decisions based on economics. Let's talk about the ease of integration of LUX. One of the best things about it is that it's really very easy to put into your operation. As I mentioned before, the workflow only adds about 4 to 6 minutes to the overall plate making process. The actual time required for lamination of a full 5280 plate is only 110 seconds. So ultimately, this has no material effect on your plate making capacity. It's not the rate limiting step, and it adds very little time overall. The equipment footprint is quite small. The 62-inch laminator that I showed a picture of earlier only takes up 22 square feet. We'll be introducing a 38-inch wide laminator very shortly that will only take up 16 square feet. The laminators are mobile and can be moved to wherever you need them or moved out of the way if you don't need them at a particular time. So there's a tremendous amount of flexibility in terms of how you situate the laminator. The other nice thing is that LUX is completely flexible. It works with all digital plates, all plate thicknesses from the thinnest of thin plates to the thickest of corrugated plates, all plate format sizes from the smallest all the way up to 52 by 80-inch plates, all digital imager types, and all exposure and plate processor types. And it's backwards compatible, which means that you use LUX when you want, but you can continue on with your standard digital workflow whenever that's more convenient or advantageous for you. So if you have a great deal of legacy work that you're using standard digital process on now and your customer is happy with that, please continue on using that. Happy customers are what all of us want to get, and so there's no need for you to change. You don't have to invest in new prepress for your legacy jobs, but for those jobs that you'd like to get the advantages available with the LUX type dot, you can make those changes then and use LUX when you need it and not when you don't. The other exciting thing for us is that we're finding that LUX is opening up a whole world of other technologies that we can now address. Hybrid screening in itself is not a new technology. It's been around for a long time. The typical knock against it has been that it can result in a kind of a grainy appearance in the highlights or as you fade into vignettes. This is due to the fact that in selecting the minimum dot choice for the hybrid screen, they can often be slightly larger than ideal, which results in this grainy effect. With the ability to form a very solid, well-structured, and small dot with LUX, this now allows us to select a minimum dot size, which is more advantageous for use in hybrid screening, and we're seeing some excellent results with use of techniques like this. In addition, LUX works extremely well with some of the other advanced prepress techniques that are coming on the market. I'll cite ESCO's microcell in particular right here. This is a really clever technology that allows you to do a very fine surface patterning, both in the solids, as shown in the upper picture, as well as even down into the tonal areas, as shown in the lower picture. The effect of this is quite dramatic and quite positive. The ink laydown is usually improved considerably, where you get simply a smoother laydown with fewer pinholes and often better solid ink density. LUX, because of its ability to hold the fine details better, actually makes a sharper image of the microcell than does a standard digital plate and works beautifully with this technique. So I hope I've shown you that there are reasons to believe that LUX has advantages in quality, consistency, and versatility that makes it worth your consideration. Ultimately, at the bottom line, LUX is simply a plate-making process that produces flat-top dots from a conventional digital plate. With its advantages, it does things for the printer and the print buyer, like improving the print quality, improving the print consistency, and reducing operating costs by expanding the options for flexographic printing versus other more expensive ones. For the plate maker, it's extremely easy to integrate into a plate-making operation, making it easy to bring into your operation, easy to use, and easy to not use when you don't need it. For all these reasons, this is why we believe that LUX is the next step in flexo printing. For more information on LUX and other MacDermid Printing Solutions flexographic plate products, please visit www.macdermid.com/printing or email us at mpsproductinfo@macdermid.com. thank you all for your kind attention, and have a great day.